Plants can provide food and even oxygen and drinking water, but bringing all the necessary nutrients can be a challenge, especially for long-term missions to remote destinations.
To sustain a long-term presence on the moon, plants need to be cultivated in situ. This approach is called In-Situ Resource Utilization, or ISRU. It minimizes the costs and the risks associated with transportation from Earth. Studies show that lunar regolith contains most of the essential nutrients plants need to grow, although some are in very low concentrations or not in a form readily available for plants, like nitrogen. Our approach investigates the feasibility of extracting key elements from lunar regolith to create a plant nutrient solution. This is performed using simulants, or Earth analogs to lunar regolith. To facilitate nutrient extraction and removal of undesirable compounds, a preparatory step is needed: beneficiation.
Our key objectives were the following. 1. Assess feasibility of aqueous leaching. We evaluated the effectiveness of using water as a solvent for the aqueous leaching of nutrients from mechanically and chemically beneficiated lunar regolith simulants, as well as from the byproducts from molten regolith electrolysis. The investigated beneficiation methods included crushing and grinding, screening and magnetic separation, as well as the use of acid and alkali leaching. 2. Identify and propose optimized nutrient extraction. The Hoagland solution, a reference nutrient solution for hydroponics, was used as a guide to identify extracted nutrients and toxins from the Objective 1 dataset. From here, we determined the feasibility of element supplementation and removal to create a viable nutrient solution. Data gathered from Objective 1 informed various sequences of promising beneficiation steps to create a second round of samples, the alpha samples. 3. Proposed system architecture for nutrient extraction. Based on data from the alpha samples and utilized processing steps, we proposed a simplified system architecture for nutrient solution extraction. The samples in the study were leached and analyzed for relevant elements using ICP-MS, with the alpha samples also including ion chromatography for select ions. It is important to acknowledge that lunar regolith simulants do not perfectly replicate actual lunar regolith, so data from our analysis would not necessarily match the actual lunar material under the same conditions. However, it can provide critical insights and better understanding of the importance of beneficiation in the ISRU context.
Here's what we found. Aqueous leaching effectively extracts nutrients from lunar regolith simulants and MRE byproducts. Mechanical beneficiation impacts extraction efficiency, while acid leaching significantly enhances it for certain elements. Combining these methods optimizes efficiency depending on the targeted element and sequence of processing steps, even including selective reduction of certain elements where needed. For MRE byproducts, combining both methods further improves efficiency. The results indicate that there are some elements missing or in too low concentration to create a complete nutrient solution directly. However, several elements were successfully extracted, like potassium, calcium, magnesium, in amounts that could serve as a supplement to a nutrient solution. This way, you can extract parts from lunar regolith and supplement it by nutrients transported from Earth, reducing mission cost and increasing self-sufficiency. The extracted elements that are not beneficial to plants could be used for other purposes. For example, aluminium could be used for gas purification and minerals processing. Lastly, the results from our experiments suggest that a beneficiation module for processing lunar regolith links to the ISRU ecosystem in several ways, facilitating systems and processes that support human presence on the moon. Our study demonstrates promising results using beneficiated lunar regolith to create plant fertilizer. Future studies could focus on optimizing the extraction conditions and process sequence to maximize nutrient recovery, as well as investigating biobeneficiation and additional applications for other extracted elements within lunar ISRU frameworks.